G'day, I'm Dr. Kev, and in this video we'll be analysing the link loads in a AA-arm suspension system. We'll be using calculations that come straight from the pages of Sir Isaac Newton, and while we're going to see a little bit of the maths involved, we're mainly going to focus on 6 insights that you can apply to your own project. Welcome to Car Design Workshop. Let's get started. The first insight is that the maximum load you're going to have in a suspension system won't be in pure cornering or pure braking or pure acceleration. It's actually going to be a combination of lateral loading and longitudinal loading. But before we get into some of the results, we probably need to have a quick look at the setup involved. For the initial results, we're going to start with a GG diagram that explains the acceleration of a vehicle. But by the end of the vehicle, we will apply it to some general car data. To simplify it for this video, we're only going to look at the loads on one corner only, a front corner. In this GG diagram, we're going to put the maximum lateral acceleration and braking acceleration at 1.2 Gs. This is quite a bit. This is a reasonable grippy tyre for a road car. And we will assume that the engine is capable of producing about 1 G acceleration in the car. Using this GG diagram, and by applying lateral load transfer and longitudinal load transfer, we can calculate the forces and moments of the tyre at the contact patch. And this is shown in this graph here, where we can see the force components for the tyre, the Fx, the Fy, and the Fz. And those are the components in the X, Y, and Z directions. Because this is a rear-wheel drive car, we'll see that the longitudinal force at the front corner is going to be assumed to be 0 during acceleration. Now in reality there would be some rolling resistance here, but that will just be the equivalent of doing a little bit of braking, so it's accurate enough for us to cap that at 0. And immediately we see an interesting result. If we have a look at the Fy component, that's the lateral component going into this corner, we see that that peaks slightly after full cornering. This is a point where there is a little bit of longitudinal weight transfer due to braking. And this in combination with still doing a fair amount of cornering means that the peak load is slightly higher. We will also see that the peak magnitude of the force occurs somewhere between the pure cornering case and the pure braking case. So straight away, it's really important that when we're designing the suspension of a car, we're not just breaking it down into a pure cornering case and a pure braking and a pure acceleration case. We really need to be looking at all of the loading that occurs between these states. Now we do want to go a little bit further than this and make sure that we can calculate all of the link loads in the suspension system. Now to locate the upright in space, we're going to need 6 links. We're going to get 2 of those from a lower wishbone, 2 from an upper wishbone, 1 from a tie rod, and 1 from the spring, which we're going to model as a solid link. And to calculate the forces in these links, we're going to apply the concept of equilibrium, where we take the sum of the forces and moments to be equal to 0, or equal to the forces from the tyre. Now this is a little bit of the maths part, so feel free to skip past this if you want to just get into the insights, and I'll try and go through it fairly quickly. And what we want here is for the sum of the forces and moments from the links to be equal to the forces and moments from the tyre. Now given that there's 6 links involved here, it's best that we do this as a matrix operation. Now because we know the geometry of the suspension system, we know the directions of all of the link loads. With these directions, we can turn these into unit vectors. And we also know the direction of the moments created by those links, which is just their positions cross product with the unit vector. So for each of the links, we will have the unit vector x, y, z components and the moment direction x, y, z components. And for those 6 links, we'll end up making a 6x6 matrix. If we multiply this matrix by the forces in the links, we will end up with the forces from the tyres and the moments from the tyres. So the general format of that is we'll have this matrix A times the forces equals the tire forces. And because we are putting the tire forces in, then we'll take the inverse of that matrix here, multiply it by those tire forces, and we can back calculate what those link loads are. Now in the past, I would normally set something like this up in a Microsoft Excel sheet. But because I wanted to do a little bit with the graphics and everything, I set it up in MATLAB. Now if we sweep around this GG diagram, we can actually calculate the link loads on all of those 6 links. And we see these links will have peak forces at different points around this GG diagram. We see that the lower links, or the lower wishbone, are the most heavily loaded components, and they're peaking at different points. We can see the spring is being loaded up as we're having a weight transfer, and the peak for that is occurring where we had the maximum total force from the tire. And out of these, the tie rod forces, or the forces going through that steering tie rod, are the lowest. And here that first insight about checking all of the points around that GG diagram becomes really apparent as we see that there are peaks at different locations. Now to make this insight and the following insights a little bit easier to visualize, I have colored a 3D model where we can track what the link loads are as we go around this curve. Now that we have the maths sorted out, let's just get stuck in all of the following insights. And the next insight involves our mechanical design. When we're designing the upright, make sure we try to fill the wheel. What I mean by this is we should space out the upright points. We want to make full use of the height available to us in the wheel. Now to show you the difference here, I've created 2 different suspension systems. One that has a really short upright where the points are very close to the center axis of the wheel, and one as we've modeled in the previous videos. And in this video, we see the differences between these 2 upright arrangements. Where the upper and lower wishbones meet at the upright, these points provide the support for an offset tire load. The further apart these points are spaced, the better they share that load. And we see this if we have a look at the graph of the link loads versus that GG diagram. We see that the upright with the smaller dimensions has significantly higher loads in the wishbones. You would, however, note that the loads in the steering tie rod and the spring are unchanged. So when designing the suspension here, I'm going to be trying to make sure that these points are as far apart as possible. And that's really just going to be limited by packaging and what can fit in the space. Now the next insight is very similar to this one, is that the dimensions and width of the A-arm really matters. We want to make sure that we space out the points on the chassis. Now to show a really extreme version of this, I've created a lower wishbone that is considerably narrower. And we can see if we compare it to the original design that the loads in that lower wishbone links are significantly higher. This is especially noticeable in the graph where we look at all of the different link loads together. Now it's important to note that we're calculating loads here, but if the loads are high, then the deflections of these A-arms are also going to be high, so we're going to end up with more compliance, which is also going to affect our geometry. And this is just bad engineering practice. We want to make sure that we're taking a careful look at our load paths. Now in a more subtle way of design here, I could take the original design and slightly change the dimensions of the wishbones to try and reduce the loads going in. And this shows the results of slightly changing the geometry of that lower wishbone. Now it's not as extreme as when we made the wishbone very, very narrow, but there is a real and noticeable reduction in the load just by a careful use of the geometry of that lower wishbone. Now, some of these changes are a little bit harder to implement in different cases, as you're often restricted by the rest of the packaging of the vehicle. But we will look for opportunities in the design to take these small but real gains. And the fourth insight is that the geometry that you use for your upright is going to have a big effect on your steering loads, or the loads in that steering tie rod. And in this, we're going to look at both the effect of a scrub radius and the effect of mechanical trail on those steering tie rod loads. Now, this diagram shows what we mean by a scrub radius. We take one line that runs through the contact patch center of the tire, and normally we'll call that the center of the tire, and we take another line that passes through the ball joints, upper and lower ball joints of the upright. Now, we're doing this on the front view, and the difference between those two lines and where they intersect with the ground we call the scrub radius. The line that is passing through the upper and lower ball joints we'll call the kingpin line, and that represents the line about which the wheel will rotate. Here we're going to apply a force due to braking, and you'll notice that that's offset from the axis of rotation by that scrub radius. And that's going to create a moment around our axis of rotation. In order to counteract that moment, we're going to need to apply a force in the steering tie rod. Now, in this analysis, we've fixed that tie rod, but the reality is that that force from the tie rod is going straight through to the steering rack and through to the steering wheel. And as we increase the scrub radius, we're going to increase this steering tie rod load. Now, the load generally peaks somewhere slightly before the peak braking, so there's a little bit of cornering on, but mainly it's a braking based load. Now, while we're looking at this for one corner only, we do note that there's two corners attached to this steering rack. And if we draw both of these corners, the left and the right hand side, and we apply a force to both the left and right hand side, we'll actually see that the forces going through the steering tie rod for the left hand side and the right hand side are going to actually be balanced as long as those forces are balanced. So in pure braking, we wouldn't expect that the driver is going to feel any force coming through the steering wheel or any torque coming through the steering wheel as a result of this. For each of the wheels, that offset force from that steering axis is going to try and turn the tires outwards. Now, the problem under braking occurs that the loads on each of the tires aren't always going to be equal. So if we have a high scrub radius and one side picks up a large force, so maybe one corner has less grip because it's hit a patch of oil or dirt or a lower grip section of the road, or one side has picked up more grip, we're going to start to see an imbalance. And that's going to mean in that braking zone, the car will pull to one side. So what we could experience is if we have uneven surfaces or bumps or anything like that going into a braking zone, if we have a higher scrub radius, we can end up with the car fighting the driver, trying to go left and right, as it is picking up different amounts of grip on the left and right hand sides of the car. To reduce this, we're going to want a low scrub radius. Now, there are some limits to this when we start to look at the deflection of the contact patch of a tyre, and that's going to be something we're going to discuss in later videos. Now, the other part of this insight is to have a look at the effect of mechanical trail. First, to define what mechanical trail is, we'd look at a side-on view of the wheel. We draw one line that is vertical through the wheel, and that'll intersect with the contact patch or the nominal center of the contact patch on the ground. And the second line we take once again through the upper and lower ball joints, and we intersect that with the ground. Now, the angle between these two lines is the caster angle, and the distance between the steering axis as it intersects with the ground and the center of the contact patch is called the mechanical trail. Now, in this case, we have the force, and we're going to predominantly look at a cornering force here, a force applied to the center of the contact patch that is now offset from the steering axis. Now, if we imagine that there's a turned wheel here, this force is going to try and straighten the wheel for a positive amount of mechanical trail. Now, we could put negative mechanical trail, which means a side load is going to try and turn the tire even more, but that would absolutely be a disastrous design decision. So the amount of mechanical trail is going to be the amount of self-centering a wheel has. Again, we're going to see that moment created by that lateral force being counteracted by a force in the steering tie rod. And as we go around the GG diagram, we get this sort of graph here. And we see that as we increase the mechanical trail, the steering tie rod forces go up. Now, the maximum of the steering tie rod load versus mechanical trail occurs a little bit after pure cornering, when we do have some of the load transferred due to braking. Now, just like when we had the scrub radius, we've got two wheels here, one on the right-hand side, one on the left-hand side. And we would note that the outside tire, due to load transfer, is going to end up with a larger lateral force applied. And the difference of that lateral force is going to mean that there's going to be a difference in the steering tie rod force on the left and the right hand side. This means in order to keep the tires turned, the driver is going to have to apply a torque to the steering wheel that overcomes the torque from these lateral loads. Now, just looking at this as the difference between these steering tie rod loads, we can see that the steering effort increases almost linearly as mechanical trail increases. It is worth keeping in mind here that we're showing this in newtons, and that with even quite moderate amounts of mechanical trail, you can quite easily increase the steering effort far beyond what a driver is going to be able to manage without a serious power steering system installed on the car. So just like the scrub radius, we're going to want to keep a fairly small mechanical trail, really just enough to provide a good sense of self-centering of those front wheels. Now, these insights into the steering system are very useful, but really only part of what we're going to have to do around that steering design. So there's definitely more to come in future videos here. Now, the fifth insight is that we can use jacking in the suspension to unload the spring. And what I mean by jacking is that we can use something like an anti-dive, which will be longitudinal jacking, or we can use a higher roll center height, which is really just a higher instantaneous center slope, to do jacking in a lateral sense. And what we're saying is that the slope of the A-arms affects the load that's going to be going into the spring. To show this, I've created another version of the suspension system that has a significant amount of anti-dive in the front suspension system. To determine how much anti-dive we would have, we would take a line that joins up the chassis mounts of the wishbones, upper and lower. We would have one line for each, an upper and lower line. We would join those together as a point, and then that point we would take through to the contact patch. And the slope of that line is going to determine how much anti-dive we have during braking. If that slope is higher, we're going to have more anti-effect. And we can see side by side with the original and a suspension system with anti-dive just how the loads are changing here. Now, this is a little bit easier to see if we take the graph of those link loads. And the most noticeable difference is going to be in the loads going into the spring, especially when there's a reasonable amount of braking being applied. And you can see the original is shown as the dotted curve here, and the suspension system with the anti-dive is shown as the solid line, and we can see that the load going into the spring is less than without the anti-dive. And this is really just because that in this loading direction, the wishbones now have more vertical component to the direction of their links. Now the same thing occurs if we look at the roll center height from the front view. Now in this video, I'm not going to discuss the pluses and minuses of whether you define a roll center or how much you use that as a concept. It's not really the point around which a car rolls, but it is a useful concept because it does give you an idea for the slope for that instantaneous center. And it's the slope of that line, or the angle from the ground to that instantaneous center, that really helps. Now to define this instantaneous center, we just take a line through the upper wishbone, a line through the lower wishbone, connect those to a point. That point then joins to the center of the tire contact patch. And if we look at this graph, we can see the spring load versus a change in roll center height. This is done just in that cornering case. And if we increase that roll center height, we can see a decrease in the amount of compressive load on that spring. And that's because the wishbones now are taking some of that vertical load. In practice, that's going to mean that the spring is going to compress less when you're going through roll than it otherwise would, which is going to act as an anti-roll effect. Now I will add one word of caution when we're doing design around roll center heights and the amount of anti-dive or anti-squat you might use. And as we saw with the first insight, we can't just look at the suspension system in isolation. We can't look at just a front view and just a side view because the loading changes between these states. When we make a change to anti-dive, we're not just going to be affecting the pure braking case, we're also going to be affecting the combined longitudinal and lateral case. And likewise, when we increase the roll center height, we're also going to have an effect in the longitudinal case, not just the lateral case. And really that leads me to the sixth and final insight I want to make based on these load calculations. And that is that when we are working with a real car, the loads are going to change quite a lot. We're very rarely going to be in this pure cornering, pure braking, pure acceleration case. With a road car, we're honestly just going to be cruising most of the time. So we're really just going to look at this as if it was applied to the car being driven in a spirited manner. And the most spirited manner you can get is probably going around a racetrack. So what I've done is I've grabbed some accelerations from some race car data. And we see that the GG diagram here is far messier than the simple one we started with. If we show this in the video with the link loads, we see that the loads of those links are changing quite rapidly. This is actually occurring in real time. If we go and take this GG diagram and turn it into the forces that we're going to see in each of these links, we see quite a pattern here. If you spend some time, you could probably isolate which parts of these is a corner and which parts of these are going to be braking and acceleration. But one thing that is blatantly obvious is the loads are radically changing. And that means as we're designing a suspension system, we can't just design it for peak cornering loads or peak acceleration loads or peak braking loads. We need to consider that this whole suspension system is going to undergo fatigue loading. Now, one way we could look at this load history is that we can take these loads and put them in a much easier to understand format where we can put it into histograms of the loads for each of these links. For most of these histograms, we see that they're roughly centered around zero load, indicating that at least on this track, there was reasonably even left and right hand turns. The fact that the spring link is always negative, it means it's always under compression, means that that spring never fully unloaded. We also notice that the links that have the largest spread of load, or are going to come under the highest fatigue loading are both in those lower wishbones, so the lower fore link and the lower aft link. And this sort of analysis can be used for calculating some of the fatigue life of different components of the suspension system. But in general, we're going to want to make sure that we're using materials and design processes that are suitable for lowering our fatigue loads. So that probably means more steel than aluminium, given that steel is better in fatigue. And when we are using aluminium, we're going to want to make sure we've got really generous fillets in our design to avoid any of those stress concentrations. So that covers the 6 main insights that I wanted to draw out of these calculations. And you probably noticed there's a couple of limitations with this. One of them is that all of the loads have been done with a static suspension system. I haven't put in the fact that the suspension is moving as it's going around corners and braking and so on. And this isn't as crazy as it sounds. We have actually had cases where we've done these calculations and put strain gauges on all of the links for a car, taken around a track, and seen pretty good validation between the calculations you see here and what the actual forces were from the real car. And that's because for most cars, the suspension isn't actually moving that much. It's still roughly in the same place. And that means these loads are probably good enough for doing our basic sizing of components, where we're already going to apply a healthy safety factor. They would definitely be more limited if we were trying to apply these loads to a handling study of the vehicle, and that's where we may actually want to mix this sort of method of calculation with some of the moving geometry that I've done in a previous video. Well, I hope you've enjoyed going through some of the implications of suspension loading and the insights that we can draw from that. And if you do like this sort of stuff, subscribe to the channel. There's plenty more coming as we go into different parts of the design of the vehicle and different aspects of suspension design. Also, feel free to put down any comments or questions that you might have. I try to get back and address those when I can. Thanks for your time.